Okay, so we're at the point where we're going to model plate boundaries using this Oreo. Okay, so we have 3 types of plate boundaries, and you just told me one of them is what? Divergent. So divergent meaning that the plates are moving apart. So in this case, your 2 halves of the cookie, right, will be together, and what you will do is you will try to move them apart, but not just pull them apart. Try to push the cookie into the filling, into the stuff in the middle, and trying to pull that apart. And you can kind of feel how the creamy filling can be like the asthenosphere, where it's kind of plasticky. Just take it, just cut it apart, and you can, yeah. So you can kind of feel how that moves underneath, right? And so with a divergent boundary, you've got the plates moving apart. And then what we're going to learn about today is what happens in between that space. Does it just become a big hole, or does something else happen? So then, what's the other kind that we're going to learn about today? Convergent. So with a convergent boundary, okay, what you're going to have is you're going to have the plates moving together. Okay, and as you kind of push, oops, I just broke mine. As you push it, you can almost see something happening. What do you guys see? If you're pushing, you can almost see that it's building up in the center there, and that's a clue as to what is going to happen, as to what kind of feature forms in a convergent boundary. Now, the last kind of boundary that we're going to learn about today is called the transform boundary. Now, the transform boundary is one where the plates slide past each other. So you can kind of imagine sliding it along. I'm going to go both ways, even though a transform boundary would really only be moving one way. So that's kind of how we can use an Oreo to show how plates move. And now we can eat the plates. So go ahead and you can eat your plate boundaries. And again, not a perfect model, but it does show the general movement. Okay? All right. All right, so on the next page, I'm starting a new page of notes because I filled up my other one. But on the next page, at the top, you're going to write our essential question for today, which is, what features are formed at different types of plate boundaries? Okay, and I'm going to highlight or put a box around the term features. So, yep, what features are formed at different types of plate boundaries? So, before we answer that question, let's do a really quick review of what we know, all right? And then we can go ahead and start learning about the different types. So the first thing I'm going to do is I'm going to review Earth's interior. So to do that, I'm going to draw what I know about Earth. So I have a small circle followed by a slightly larger circle, and then you want a much larger circle in comparison. So these represent the various layers of Earth. And on the outside of the Earth, we have our crust. But I'm going to draw the crust a little bit different from how I've drawn it in the past. I'm actually going to show it with our plates on it. So the plates rest on top of the mantle, forming boundaries in between them. So I'm kind of exaggerating those boundaries, but so we know that right on the top we have the crust. Okay, these are tectonic plates. All right, so now the crust, we know that this is the thinnest layer. It's also cooler than all the rest, and it is brittle. Okay, so brittle meaning it breaks easily, kind of like our cookie did. So we have our crust. Now, the crust sits on top of what layer? The mantle. The mantle is the thickest layer. It is semi-solid, and we say that it's sort of like plastic, and it behaves like plastic. So in other words, it's not brittle like the crust, it gives. It has some give to it, all right? So the mantle. Then we go in another layer. What's this? This is the outer core. So the outer core is made up of what? Liquid metal. Okay, now the outer core is the only layer that is actually liquid, right? The mantle, it has movement in it, but it is not a liquid, okay? It sometimes can behave sort of like a liquid, but it's not a liquid. And then finally, you have the inner core. And at the inner core, this is where we have the hottest part of the earth. It is solid, and it is metal. Now, why is that solid and the outer core is liquid? It all has to do with pressure, okay? This is due to the immense pressure that occurs in the center, okay? Now, the other part of my diagram that I want to label is the part that is in between the plates. And this is the part that is called plate boundaries. And plate boundaries, this is where two plates meet. Now, let's talk a little bit more about those plates, okay? And to do that, we need to talk about the crust and what makes up the crust. So, we have two types of crust. Who can tell me what one of them is? Oceanic and continental. Those are the two. So, oceanic, and then over here I'll do continental. All right, so what do we know about oceanic crust? We know that oceanic crust is thinner than continental, and it is dense. We also know that oceanic crust is made of basalt. Now, on the other hand, continental crust we know is thicker, and it is less dense. In addition, it is made of granite. So as we go through this lesson today, we're going to be drawing representations of both basalt and granite, or oceanic crust and continental crust. So what's that going to look like? When I draw an oceanic crust, I'm going to draw it thin, okay? As opposed to my continental crust, I'm going to draw it visibly thicker. I'm also going to use a different color combination. So I'm going to use blue for my oceanic crust. You don't have to use blue. You can use whatever color you want. You just have to be consistent. I'm going to use green for my continental. So just so we can differentiate between them easily. Okay, so there's kind of like, that's your key for your drawings to come. All right, so moving on, we are going to start talking about our 3 types of plate boundaries, and I'm actually going to start with the transform boundary, and the reason I'm going to do that is because there's only one kind that we're going to talk about for the transform boundary, so I have just enough space here at the bottom to do that. So now this is a draw with me kind of lesson, right? So you're drawing what I'm drawing to the best of your ability. I've had some practice to draw some of these things, and I'm still not real great at it, but you know, don't get frustrated if like you can't keep up or yours doesn't quite look like mine. You can always, you know, find, you know, borrow my drawings later or go back and, you know, watch this video. This video will be on Google Classroom, so you can have, you know, like a repeat if you need to see it again. So I'm going to, every time we talk about a new boundary, I'm going to give it a heading. Then I'm going to use arrows to kind of help me remember what's happening with this type of boundary. So for a transform boundary, I'm going to use arrows that are each, they're on top of one another, and they're pointing in opposite directions. For my arrows throughout this, the drawing, I'm going to use red. Again, colors, you don't have to match my colors. You just want to be consistent. Okay. So remember that at transform boundaries, the plates are going to slide past one another. So here's how I'm going to draw that. I'm going to try to draw two slabs of crust, basically. So the first one that I'm going to draw on the top is going to look like that. And then I'm going to draw the next one over, like shifted over a little bit. So it looks like it's moved from its original location. If you feel like it, you can even kind of make it look three-dimensional or not. Okay, and then what you want to show is you want to show that one of these is moving in one direction and then the other is moving in the other direction. So I have plate 1 and plate 2. Now I'm going to color these in green. Now the thing with a transform boundary, one thing to take note of, okay, these arrows are showing relative movement. What this means is only one of these plates may be moving. So let's say of these plates, 1 and 2, only 2 might be moving. But the relative movement of them is what is shown by the arrows. Okay, so the one on the top appears to shift to the right relative to one on the bottom, which is shifting to the left. So now for each type of boundary, what I'm also going to tell you is I'm going to tell you what are the effects and at least one example. Okay, so the effects of a transform boundary is that we have plates move past each other as though they're sliding kind of past each other in opposite directions. Now we talked about there's a the example of the transform boundary we're going to talk about is the San Andreas Fault, which I showed you a map of the United States in our last class that shows you where there's a high risk of something happening. Do you remember what that natural disaster was? Earthquakes. So earthquakes are common at these locations, at these boundaries. But, side note, an earthquake can happen at any plate boundary, okay? But they happen frequently in a transform boundary, and they can be much more devastating. All right, so those are the effects. And the example I'm going to use is the San Andreas Fault in California. And in future lessons, we're going to talk a little bit more about the San Andreas Fault so we can learn a little bit more about it. But for now, just know that that's an example of a transform boundary. Okay, so I'll give you a minute just to finish copying that down. And then I'm going to turn my page. Okay. All right, so now we're going to get into another type of plate boundary. And for this, I think we're going to go to divergent next. So for divergent, I have two examples of divergent boundaries. So at the top of my page, I'm going to write divergent and I'm also going to use arrows to show what's happening at a divergent boundary. So I'm going to have one arrow that's pointing to the right and one arrow pointing to the left. And what that's showing is it's showing that at this plate boundary, the plates are moving away from one another. Okay, and oops. So two plates pull apart. So the two types of plate boundaries we're going to talk about have to do with the type of crust that is involved. So the first type we're going to talk about is an oceanic divergent boundary. So oceanic means both plates are oceanic crust. So oceanic divergent. So to start my drawing, I'm going to draw some water. Beneath that water, I'm going to show that I have an oceanic plate on one side, another oceanic plate on the other. And I'm going to show that I've got movement away. So these are moving away from each other. Okay? Now, you might think that in a divergent boundary like this, it's natural to think that what we're doing is we're forming a hole. But that's not what's happening. Actually, just the opposite. What's going to happen here is as these plates move apart, what's going to happen is magma from the mantle is actually going to move up into that space. And that's because of the density. So this less dense hot magma is going to move up and it's going to fill in this space, and it's going to form mountains, underwater mountains. I'm going to color in. And then what I want to show here is that there is magma that is pushing up into that space. Okay, so magma moves up and fills in that space. And then when the magma comes to the surface and it's hitting the cold environment around it, the magma cools and it forms rock. It forms more basaltic rock. And this ends up creating an underwater mountain range. Okay, so the effects of an oceanic divergent plate boundary. First, we have new crust that is formed. Brand new crust. As that magma comes up, it cools, it hardens, it is now part of the crust. Secondly, we have a ridge that forms. And we call this process seafloor spreading. So in the middle of the Atlantic Ocean, we have a ridge that runs north to south. It actually goes right through Iceland. It's breaking Iceland apart, actually. And that is actually called the Mid-Atlantic Ridge. So what's happening is, in the middle of the Atlantic Ocean, you've got this ridge, and it is spreading apart, and there is new crust forming as we speak under the ocean. So the example we're going to use is the Mid-Atlantic Ridge. And we will definitely talk more about that in a little more detail specifically. There are other ridges in the bottom of the ocean, but the Mid-Atlantic Ridge is one that is very well known. Okay, so now we're going to go on to our next type of divergent plate boundary, and that has to do with continental crust. So in this case, it's called a continental divergent. Okay, now for this one, remember continental is less dense, right? It's not going to happen underwater. So this is think of on land. Now to draw this is a little tricky to draw. You might just want to kind of watch me first. And sometimes when I do this, it ends up looking really good and sometimes it doesn't. So just kind of bear with me. It's kind of like a backwards slanted 7. And you kind of keep doing that. And then you do the same thing on the other side. It'll make a little more sense once I finish here. And so then we kind of show how these are connected. And then I can color it in, and it's sort of, you still may not be able to see it, and that's okay. These are two continental plates that are pulling apart from each other. I'm coloring them in green because that's my code for continental. And then I'm going to color in front of it too. So can you kind of see it now? where it's like they're like cliffs. And so if you kind of imagine that these are moving apart, right? These are plates that are moving apart. And what do you see forming in between these two plates? A ravine or an open space, right? A rift, a valley rather. This is actually called a rift valley. So a rift valley is formed. Okay? And there's actually something else kind of cool that can happen. So we know that for effects, it widens over time. It forms rift valleys. And it could form what we call linear seas. I'm going to give you an example of that to help you to visualize it. So what could happen is, and it doesn't all the time, but what could happen over time is this could fill with water, okay? And so it could form a sea. One example is the Red Sea. The Red Sea is a very long, narrow sea, and that was formed by a rift valley. So that's going to be one of my examples. The Red Sea. And my second example is going to be the East African Rift Valley. And again, we're not going to go into a lot of detail on these examples right now, but we will talk about them more later. So those are our two types of divergent boundaries. The last type of boundary we're going to talk about is a convergent boundary. Of the convergent boundaries, there are actually three types, two of which are pretty similar, all right, and one is different. So I'm going to do that on a new page. So convergent. So for my convergent boundary, I want to draw my arrows to indicate that the plates are moving together. So here's my arrow going this way, and I'll do the basically same thing over here, just facing each other. So here's plates moving together. So two plates collide or come together. Now, one point that I want to make is, like, when these plates are moving, it's not like the continental plates are like smashing together, okay? This is something that happens very slowly, and the effects happen over long, long periods of time. So this first one that I'm going to show you, which is called a continental-continental convergent boundary, results in some pretty cool stuff, or a pretty cool feature, but it's not something that happens like overnight. None of this happens overnight. All right, so this one is hard for me to draw. I'm going to admit it, but I'm going to do my best. Okay, so what I'm going to do is I'm going to draw my continental, my two continentals kind of coming together. But what ends up happening is once they come together, right, they can only do certain things. One either has to go below the other one. And in this case, that doesn't happen because it's continental. So what ends up happening is they kind of smush together, and then the rock ends up going upward. Okay. So it kind of, I'm going to try to show like how the motion happens. This kind of, there is some that goes down too. But what ends up happening is you end up creating these mountains that are pretty jagged. That is a terrible picture, and I apologize. But I think you kind of get the idea. The plates are moving this way. And I have continental plate for me is green. I'm just going to shade that in quick. All right. That's good. Okay, so the effects of a continental boundary. We have mountain ranges. And the example or examples that we're going to use, the first one I'll use is the Himalayan mountains. Himalayas is where we've got the highest mountains in the world. They are very, very high, and they are jagged. But another example is the Appalachian Mountains. Now, the Appalachian Mountains here on the eastern United States actually started out looking just like the Himalayas. Very jagged, all right? But over time, they have rounded out, and they're much less jagged. Why do you think that is? What could have caused those to round out? Erosion, yeah, weathering and erosion, and a lot of time. The Appalachian Mountains are really old, okay? So they started out, Appalachian Mountains started out looking like the Himalayas, but they don't anymore because of all that weathering and erosion over time. All right, my second example is we're going to do continental oceanic. So this is where a continental plate collides with an oceanic plate. All right. So now, this one's fun to draw. I'm going to do some water. Okay, because this is like at a shoreline type of situation. And then to the right, I'm going to have a thick continental crust. And then I'm going to have, on the left, I'm going to have a thin oceanic crust. Okay, so we know that the oceanic crust is going to be more dense than the continental crust because it's basalt versus granite. So the result of that is that the basalt is going to subduct beneath the granite. So what will that look like? What will happen is this will plunge down beneath that continental plate. Now, one thing that'll happen here, and I exaggerated it a little bit, okay, but, well, a lot, but this is what we call a trench, all right? So a trench is going to happen. It's, great expanse of space that, lots of life will live there and everything. And then what's going to end up happening is this crust that has gone below the continental crust is going to be subjected to a lot of heat. It's going to be hot down there. And so what's going to happen is it's going to melt, okay? This plate is going to undergo melting. Okay, so that material that melts now, it's going to be hotter than the surrounding material, and therefore we know that hot things and hot fluids rise above cooler ones. So what's going to happen here is you're actually going to form magma that's going to rise through the crust. And what do you think might form up here on top of the crust? Volcano. Yep, a volcano. So I'm just going to do some color coding here. I want to show the melting with my magma. So that plate subjected to a lot of heat. Okay. Might have some, let's see, I'm going to do some smoke. I'm going to color in my oceanic and my continental. Don't forget to color in my volcano. So this is volcano, okay? And I just want to also put in an explanation of what happened here. So this plate was forced down into the mantle. Okay, and that's where it is exposed to that heat. That's where we have the melting, and then we have rising basaltic crust or basaltic lava that comes up, and it forms your volcano. So the effects, again, we have trenches, we have volcanic mountain ranges. And for examples, we have the Andes Mountains in South America, and we have the Cascade Mountains in western United States. So there's your effects and your examples. We have one more to go. We're doing really good. I'm just going to move this up a little bit. Okay, maybe I have just enough room. What do you think the last one is? It's oceanic, oceanic. You got it. Oceanic, oceanic. Convergent. All right. Okay, this one looks pretty similar, except that it happens, most of it, underwater. Okay, so we're talking about kind of middle of the ocean type thing. All right, and I'm going to, over here, I'm going to have my oceanic plate, and I have my other oceanic plate. Okay, now, if these plates are both made of basalt, right, then they're both considered denser. So what's going to happen is whichever one is more dense for whatever reason, that is the one that's going to subduct. Okay, so I'm going to say that this one over here has a higher density, and that's the one that is going to subduct. So again, we're going to kind of draw it plunging beneath this other plate. So again, you're going to have the forming of a trench. All right, similar to what happened with our continental oceanic, you're going to have melting. Now, you're also going to have those plumes of magma. What do you think is going to form here? What's that? Okay, close. You said underwater volcano. It's actually going to be not underwater. So you notice how it comes up? It's an island. Yes, it's an island. I know that doesn't really look like an island. Anyway, okay. All right, so I want to so it's a volcanic island arc. That forms here. So the effects, we have, again, trenches, and we have volcanic island arc. So it's kind of like a chain of islands that forms. So, for example, an example of this would be the Aleutian Islands. And again, not going to really go into the details or into the examples right just yet, but we will. All right. So very similar to the continental oceanic, it's just that, you know, one of them happens underwater and ends up forming an island as opposed to the other one that forms like more of a coastal volcanic range. So those are our 3 convergent boundaries. So today you've learned basically 6 specific types of boundaries that are of 3 different types. So we will continue to review this, and one of the activities that we're going to be doing starting next week is actually a project where you're going to be able to model these, and you'll have a choice of which one you might want to model. It'll be a partner in-class project, so we'll get that started next week. So, review the video, review the notes as needed, and we'll go from there.